Hi, guys. Okay, let's finish chapter 4, which is on atoms, and we are looking at the isotopes and how to calculate the average atomic masses of the isotopes. Then we're going to look at the electronic configuration in a lot more detail, and then the trends in the periodic table. So first of all, let's look at the isotopes. So what is the meaning of isotopes? Iso means same, and topes, T-O-P-E-S, and I just, look at the P, it means the same number of protons. So those elements that have the same number of protons, but different number of neutrons, then those are called the isotopes. Now, what are the examples of isotopes? For example, you have magnesium, okay? Magnesium 24 and 12, okay? Another magnesium is 25 and 12. And then the third one is, sorry, this is magnesium G, 12. And the third one is magnesium 26 and 12. So you see here, 12 represents the atomic number. And this atomic number, as we discussed in the previous video, this atomic number is equal to the number of protons. And the number of protons is also equal to the number of electrons. Okay, so keep that in mind, that the number of protons, or that is equal to the atomic number, that defines the identity of the atoms. So atomic number defines the identity of the atoms. So we see that the 12 is always going to be associated with magnesium. But if it is 13, then it becomes aluminum. And if it is 11, then it becomes sodium. Okay, so it's the whole thing changes about it. So that's one piece. Now look at, so this is the atomic number. And this atomic number is 12. And so we talked about its number of protons, and the protons that determine the identity of the atom. So that's one piece. Next comes the number of neutrons that are different. So how do we get those number of neutrons? So we talked about in the previous lecture, and this is again a review of that the number of neutrons is equal to the mass number minus the atomic number. Okay, mass number minus the atomic number. So in the case of, let's do this again. In the case of magnesium 24, magnesium 25, and magnesium 26. And all of them have 12. So the number of protons, number of electrons, mass number, and the atomic number. And then comes the number of neutrons. Okay, so we see here that the number of protons is 12, number of electrons is also 12. So 12 is common to each of these elements. The only difference is the mass number is 24 atomic mass units. The mass number is 25 atomic mass units. The mass number is 26 atomic mass units. Okay. Then comes the atomic number. Atomic number is, in this case, 12, in this case, 12, and in this case, 12. So what is the number? How many number of neutrons? So 12 minus 12 is 12. The number of neutrons on the other one is 13. 25 minus 12 is 13, and 26 minus 12 is 14. Okay, so I'll put this here really small, that 25 minus 12 is equal to 12. Sorry, 24 minus 12. 24 minus 12. This is 25 minus 12, and that gives you 13. And this is 26 minus 12, This is giving you 14. So this is how you get these number of neutrons. So the main weight of the atom is due to the nucleus. So here is this nucleus in the middle, and this nucleus contains the protons due to which there is a positive charge. Neutrons are neutral, no charge, and outside the nucleus are these energy levels, and this is where the electrons are found. So for a neutral atoms, the number of protons and the neutrons have to be the same. Okay, now we have in this energy levels is where you are going to find the electrons. So electron here, and electron here. Okay, depends, how many electrons are there. So this is just, I'm repeating this. So this is a 2D model of an atom, atomic structure. Okay, so this atomic structure is very like a general. This is a very general structure. And then the more complex one we will study in a minute. But when we talk about the isotopes, we are talking about, the same element, but which has atoms, the ones that are weighing differently, which are weighing heavy. So obviously, because this one has more neutrons, so it's going to be heaviest. This one is going to be heavier than this guy. Okay, so the heavier the nucleus is, the more unstable it is. So keep this in mind, that heavier nucleus is unstable. Unstable means it's degrading. It is unstable means it is decaying. It's going through some process of disintegration. So due to this disintegration, the nucleus is like becoming, because it's a heavy nucleus, it's shedding its weight and it's turning into something else. So that whole process is radioactivity. That is due to radioactivity, the elements, they, change their nucleus changes. So basically coming from, more radioactive, unstable state to a stable state. And we will study about this more later, but here, once it becomes stable, then it's not heavy that more. But then it's not the same nucleus, it's something else. Okay, so anyways, we will study about this. Hold on to this. This is in chapter 5 on nuclear chemistry. So we will study this. But for now, just focus on one thing, and that is the focus on, when we put the, so if it is like, okay, look at all these numbers. These are all exact numbers. These are exact numbers. 12 is an exact number, right? 12 is an exact number. Exact numbers. This is mass number. This is again exact number. Atomic numbers are the exact. And even the number of neutrons is an exact number. But when you look in the periodic table, you see magnesium's weight is written as, 24.31. 24.31. So the mass number of magnesium, where is the decimal coming from? If you just add what is a mass number, the mass of magnesium. The mass of a magnesium is mass of magnesium, or generally the mass of any atom is, any atom is, you take the number of protons and you add the number of neutrons. Okay, that's going to give you the mass number. So it should be a very simple, straightforward, exact answer, exact number, right? It should be. But what we are doing is we are taking the mass of magnesium 24, mass of magnesium 25, mass of magnesium 26, and we are averaging it. We are taking the average atomic or average mass numbers. And how do you get them? That is of the isotopes. So we will combine these. So here we have also brought in another thing. Okay, and that is related to abundance factor. Abundance factor. Okay, abundance factor. Now, what is abundance factor? Each of these magnesiums that are found in the nature, magnesium 24, magnesium 25, and magnesium 26, they are found in some amounts in nature. Magnesium 24 is more like readily available. It's more available. It is more like magnesium 24 is more like abundant. Okay, more samples of it are going to be found in nature. But magnesium 25 and magnesium 26 are found in lesser amount in nature. Partly they are radioactive. They are also undergoing, they are unstable. So we talked about this thing is that these guys are unstable. So they are decaying. So that's how they lose their identity. So they're not there anymore, like they've turned into something else. So once they become another stable element, then that's it, that's the end of it. But for now, we can't ignore their presence. So how do we do this? So we see that magnesium abundance factor, let's write this down. And how do you calculate if you include the abundance factor, then how do you do the calculations? So here is this abundance factor of magnesium 24. So magnesium, one second. So here, let's look at, okay, actual mass of the isotopes, actual mass of the isotopes. Okay, let's do this. So 78.70%, okay, magnesium 24 that we call, and that is actually available in nature as 23.99. Okay, so all we do is multiply this, and that gives you the, then you take the masses, you add the masses from the individual samples. Okay, next is 24.99. 24.99. This guy is present as 10.13%. Okay, and 11.17%, this one is present as 25.98. Okay, so this is magnesium 24, this guy is magnesium 25, and this one is magnesium 26. So, casually rounding up, we talk like that. But when you multiply, then this is how you calculate this. So this means 0.7870 times 23.99. The other one is 0.1013 into 24.99. And the third one is 0.1117 into 25.98. Okay, so let's do this math and let's get the answers. Okay, so when we did this math, we found that 18.88 comes when you multiply 0.7870 and 23.99, and then 2.531 is obtained when 0.1013 times 24.99 is multiplied, and then 0.117 times 25.98, when that is multiplied, you get 2.901. When you add these up, all these comes out to be 24.31. Now, this is the atomic mass unit. So this is the average mass of all isotopes. Okay, average mass of all the isotopes. And this is what we put in the periodic table. Okay, so this is one piece. And just to show you a little bit of this here, what does this mean? So this is 78.70 divided by 100. Okay, and that is giving you 0.7870. Okay, just so you know, this is a little piece on the side. How did you get these numbers? How did you get this number? How did you get this number? And how did you get this number? This comes when you solve these. This is basically divide by 100. This number divide by 100. And that gives you this number and the other number, same way. Okay, so we see that the average atomic mass of all the isotopes, because we have factored in or included the abundance factor, it will have the decimal in it. So pretty much every element that you see in the periodic table has a decimal to it, and that's where it's coming from. Okay, now let's look at the study check. Study check of, let's see, 1 minute, isotopes. So let's do one study check. Study check problem 4.5, and this is on page 118. All right, here. So we see vanadium is a micromineral needed in the formation of bones and teeth. Write the atomic symbol of this single naturally occurring isotopes of vanadium. So the question is, write the symbol. So the symbol for vanadium is V. So this is something, you know, you should memorize. And if not, at least you should know where to look at. Okay, now it's 23 and 50.94. So it's 23 and 50.94. Okay, now comes the second question here. Write the atomic symbol for the single naturally occurring isotope vanadium, which has 27. So it has got 27 neutrons. Okay, and it will have 23 protons, and it has 23 electrons. Okay, so this type of question can be asked, you know, write the symbol of this element and that element and so forth. All right, next is, let's look at another study check problem, which is 4.6. So study check 4.6, and this is on page 120. Okay, so here we have, there are two naturally occurring isotopes of boron. Okay, boron. Make sure you know the symbols of the elements. So boron, the isotope B10 and 5. So like I said, you can write it like this, you can write it like this, or you can write like this. It doesn't matter. All are correct, you know, or even sometimes you will see it's like this, you know, that's also fine. Okay, anyway, the isotope B10 and 5 has a mass of 10.01. So here B10 and 5 has a mass of 10.01 atomic mass units. Okay, with the abundance of 19.80 and the abundance factor. Okay, and I'm going to just put this here. Abundance factor is AF. So, you know, I don't have to write this again and again. So abundance factor in this case is 19.80, 19.80%. Okay, and the isotope of B11, 5, and that one is, the mass has a mass of 11.01, 11.01 atomic mass units. Okay, with an abundance of 80.20. Abundance factor is 80.20%. Okay, so calculate the atomic mass of boron using the weighted average mass method. So this is another thing that they also use called the weighted average mass method. All right, so now we are going to look at the, so let's just set it up. So boron 10 and boron 11. So we have 19.80% times 10.01 is equal to, 0.1980 times 10.01. And the other one is 11.01 atomic mass unit. Sorry, let's just do this. The other one is 80.20. 80.20% times 11.01. And this is 0.8020 times 11.01. Okay, so let's do these calculations. Okay, so we take the abundance factor times the mass number, and you take 19.80 as we discussed, 19.80 divided by 100, and that gives you 0.1980. Okay, similarly 80.20, when you divide that by 100, and that gives you 0.8020, and that's the number you are basically multiplying by the given mass numbers of each of the isotopes. So in this case, it's boron. So when you do the math, you find that 1.981 comes out when you multiply the abundance factor 19.80 times 10.01, and then 8.830 comes when 80.20% is multiplied by 11.01. So in that case, you will see now when you add these two, you get 10.81102 and so forth. Now let's also discuss these significant figures. So whenever you're doing these calculations, then you pay attention to significant figures. It's very important because that's something that we put in the periodic table. So we want to be as much, exact or accurate and precise as is possible. So here we have 4 significant figures, and here we have 4 significant figures, and we are multiplying. So this answer obviously will have 4 significant figures. Okay. Similarly, this is 4 significant figures. This is 4 significant figures. And similarly, this answer should have 4 significant figures. Now, when you add, this is 3 places after the decimal, and this is also 3 places after the decimal. So we need to have 3 places after the decimal. Okay, because adding is that. Now, here is ideally your answer is 10.811 atomic mass units, 3 places after the decimal when you add. But sometimes, in the periodic tables, publishers, they want to have like 2 decimal points. That's like a little bit, easier for them for the matter of space, and in general, in chemistry also, 2 decimal places are considered to be like normal. Okay, normal. So the number that you see, the answer is 2.81 atomic mass unit. Okay, that is the number you should see. Let's see. Yeah, that's the number you see in the periodic table for boron. Mass number of boron is listed as this. Okay, so this was the example of a study check problem. Now we are going to look at the electronic configuration. Okay, now just give me 1 minute over here. Okay, so now let's look at the electronic configuration. So first of all, as we were talking about, that the structure of atom we have been discussing is that it is containing a nucleus which is in the center, and the nucleus has the positively charged protons, and it also has the neutrons, and this is forming the main bulk of the atom, and that is called a nucleus, and it's in the center, right? And the positive charge, as many number of protons are there, as many positive charges are going to be there. Okay, so that's one piece. Now we know that outside, the electrons are found outside the nucleus, and they are found in the energy levels, and these energy levels are are these regions in space around the nucleus where the electrons are spinning, and the electrons are rotating and spinning on their axis. And yeah, this seems like a very easy, very simple diagram. But the reality is that this is not the real structure of atom. The real structure of atom is this, and this is fine. It still has the number of protons and the neutrons. It is still called a nucleus. However, the energy levels are not like this, the way I have drawn. This is just a 2D model, which is very simplified version. The reality is that these energy levels, they overlap. As you increase the number of protons, the number of electrons are also going to increase. So that means the atom is becoming bigger and bigger and bigger. So it needs more space to keep not only the protons, but also the electrons. So where are those electrons placed? And if you have a mess like this, it's difficult to find it's difficult to locate the electrons, right? Where exactly is the electron? In which energy level? How far from the nucleus? Fine, we understand. So Bohr's model was just to deal with hydrogen, one atom, and then that atom contains only one proton, and it contains only one electron. So it was easy to place it. Then come helium, then come lithium, like baby elements, baby atoms, very little electrons. So 2D model explained them. But as we started getting more and more energy levels added to it, then this 3D model made more sense. But the challenge was to determine where exactly are the electrons located, right? So in which energy level, or what is, so to give this whole mess, to give more like a more what do you call, a more structure, organization to this mess, mathematics has been used, right? Schrodinger's wave equations, Heisenberg, principles, Horn's loop, Pauli's exclusion principle. All these scientists, they came up with their mathematical, calculations to prove that where exactly is the electron and how to locate it. Is just like you have people, right? Just like you're trying to locate someone, a person, and that person is in you're trying to find that where is that person located, right? You first look at that person, like which city does that person belong to, right? And in the city there are streets, right? So in those streets, there are numbers of the street. So that number of the street tells you, that person's, address. And then you look at the house number. If you want to send some gift, or you want to invite them to a party or something, then you look at their exact location, which is based on the city, the street, the house number. House number is like an apartment, whether it's a 1-bedroom apartment, whether it's a 2-bedroom apartment, whether it's a townhouse, whether it's a house, right? Small house, big house, mansion, those things. So apartment or a house. And then in that house, like let's say if it's a dorm, if it's a dorm, then how many people are living there? Roommates. So how many are in there? It's a 1-bedroom house or like 7-bedroom house, those things. Okay. Anyway, so now we have here, just like you locate the people based on their address, similarly, we are trying to locate the electrons based on this address kind of, thing. So every shell has a subshell, means every big, so this shell is basically the main energy level, and this is also called a principal energy level. Okay, next comes the part of that energy level, which is called a subshell. And the subshell is, so this is two types. So one is the name, and the other is the, one is the name and how many, yeah, type and the number. So how many, so the name and how many streets are there in a big city, right? The more the streets there are, that means the more bigger the city is. So then every street has a name, like that. Similarly, houses, there are apartments, have names, right? Names and how many houses are there on the street. Okay, and then how many people can live. So this relates to, people, how many people. So that's just equation. Okay, so now let's look at it. The energy level one, okay, it has got only one street. It's a very small place. It's a very small energy level. So it has got only one street. And what is the name of that street? The name of that street, or the name of that subshell, is 1s. Okay, how many houses does it have? It has only one house. What is the name of that house? The name of the house is 1s. So the name of that orbital is 1s. How many people can live in one, like, small 1-bedroom apartment? 2 people maximum. Okay, like that. Okay, next is the energy level 2. Energy level 2 means how many streets there are? 2. If the big, subshells are 2. What is the name? The name is 2s and 2p. Actually, I should have flipped it. Just give me 1 minute. All right, so I just flipped it. So here's the thing. So let's look at this. This is a one city. Let's start all over again. So energy level 1, that is one subshell number 1. How many subshell? Shell number 1. How many subshells? Only one subshell. What is the name of that? It is 1s. Okay. How many orbitals are there in that? It's only 1. The name is 1s. How many electrons can be accommodated? 2. Okay, so this means it's a very small city. It has got only one street. The name of that street is 1s, and the name of how many how many houses are there? There's only one house. Name of the house is 1s. How many people living in that house? Maximum 2. Next is a little bit bigger house, bigger town, like, bigger town. So how many streets are there on that? 2 streets. What is the name? 2s and 2p. 2s and 2p. Okay. How many orbitals or how many houses are there on that street? So this one is 1 and this one is 3. Slightly bigger street. Okay. The name is 2s and 2p. How many electrons can live in 2s? 2. How many electrons can live in 2p? 6. Okay. So this is a slightly bigger. So that's, this has all been mathematically proved. Next is the energy level 3. Energy level 3 is made up of 3 subshells, or the energy level is also called a shell, made up of 3 shell. The third shell is made up of 3 subshells. What are their names? 3s, 3p, and 3d. Okay. Then how many orbitals are there in 3s? 1. How many orbitals in 3p? 3. And how many orbitals in 3d is 5. What are their names? 3s, 3p, and 3d. How many electrons can live in 3s? 2. How many electrons can live in p? 6. And how many electrons can live in d? 10. Okay. Next is the energy level 4, or shell 4. How many subshells? 4 subshells. What are their names? 4s, 4p, 4d, and 4f. Oh, I need some more space here. Let me just make it smaller. Sorry. 1 minute. Okay, so this is 4s, 4s, 4p, 4d, and 4f. Okay, 4s is made up of how many orbitals? 1. P is made up of how many orbitals? 3. D is made up of how many orbitals? 5. And F is made up of how many orbitals? 7. 1 S, so the name is 4s, 4p, 4d, and 4f. How many electrons in 4s? 2. How many electrons in P? 6. How many electrons in D? 5. And how many electrons in F? 14. Okay, so that is the, this has already been verified. So the more the energy level is, the more the subshells are. The more the subshells are, the more the orbitals are. The more the orbitals, the more the number of electrons. So if you look at it, this is 2, this is 8, this one is 18, and this guy is 32. Maximum, 18 right here. So 18 maximum total number. Okay, this is one piece. Second thing is, if you look at one thing here, 1s, no matter where it is, whether it's in the first energy level or second energy level or third energy level or fourth energy level, it doesn't matter. It will always contain 2 electrons, 2 electrons, 2 electrons. You see that? Next pattern you see is the next pattern is the P. So the P starts from the second energy level. So in that P, whether it belongs to the second energy level, third energy level, or fourth energy level, it will always contain 6 electrons, 6 electrons, and 6 electrons. Okay, now look at the energy level D, which starts from the third energy level. So D orbital, sorry, not the energy level, D orbital starts from the third energy level. So D orbital will always contain 10 electrons, and it is found in the third and the fourth energy level. Sorry, this is, why did I write 5? I'm sorry, this should be 10. Okay, let's do this again. So this is 2, this is 6 electrons. D will always have 10 electrons and F will always have 14 electrons. So D is here. We have this here. D starts from the third energy level and the fourth energy level. So D, no matter if it's in third or fourth, doesn't matter. It will contain always the 10 electrons. Okay. So this is something we see that these are the, one second. All right, now we see one thing here. Let's just write down these patterns, that the S, P, D, and F. S, no matter where it is, will hold 2 electrons. S orbital, okay, let's put this here. Orbitals. So these are the patterns. And the pattern is, if you look at it, the S will always contain 2 electrons. So this is what we are trying to put it on the side, 2, 2, 2, and 2. Okay, so S orbital, let's put here, S orbital will have 2. P orbital will always contain 6 electrons. Let's put this here, electrons. So P orbital, no matter whether it is in 2, 3, 4, doesn't matter. It will always have 6 electrons. D will always have 10 electrons, and F will always have 14 electrons. That's the maximum capability. Okay, that's one relationship we see. Next thing you're going to see is, let's just put this here, for the P is 6, P is 6, P is 6. So here's the P, and then comes the D, which is starting from the third energy level. So that's the D, and then the fourth is F, which is right here, this one. Okay, so this is one thing. Next is, let's look at the subshells. Subshells, or these are also called as sublevels. So subshells. Okay, so we see that shell number 1 will contain one energy level. Shell number 2 contains 2 energy levels or 2 subshells. So let's do this here. Shells, the relationship between the shells and subshells. Shells and subshells. So we see shell number 1 will have 1 subshell. I'm going to just put it SS. Subshell is S dot S. Okay, so don't have to write this again and again. Shell number 2 will have 2 subshells. Shell number 3 will have 3 subshells, and shell number 4 will have 4 subshells. Okay, so that's one piece. And where are they? As you can see that the 1 is 1, 2 is these 2, right? 3 is these 3, 4 is these 4. Okay, so that's one thing. So this one is this. So that's what 1, 2, 3, and 4, and that many four subshells. 4 is equal to 4 subshell. I didn't write here 4 subshell. Okay, 4 will contain 4 subshell. Okay, then the relationship between, so another thing is something common. The subshell and the orbital numbers are the same. So 1s subshell and 1s orbitals, 2s subshell, 2s orbitals, 2p subshell, 2p orbital, 3s subshell, 3p, 3d relate to these guys. 4s, 4p, 4d relate to the subshells coming from the subshells, and the orbitals, their names are the same. Okay. Yeah, that's another thing is, yeah, the another piece is the subshells and the orbitals. So the first one was the orbitals and the, so subshells and the orbitals. Yeah, so subshells. Okay, first subshell will contain 1 orbital. So in other words, S subshell contains S subshell contains, if anything is S, it will contain 1 orbital. An orbital, I'm putting it as ORB. Okay. P subshell contains 3 orbitals. Okay. D subshell contains 5 orbitals, and 7 subshell contains, DF subshell contains 7 orbitals. Okay, 7 orbitals. Okay, so this is very important piece right here. Now comes the shapes of these orbitals. So if you look at it, this is in 3 dimensions. Now when we do all this, why did we do this? Because we wanted to study the location of the electrons, and we wanted to study their placement in 3D. So this is the 3D model, is all jumbled up, but 3D, we are trying to give the meaning, to this electrons. Okay, now in 3 dimensions are like this. So we have horizontal, we have vertical, and we have diagonal. Okay, so that's the planes. So this is the horizontal plane, vertical plane. Our world exists in 3. vertical. Vertical is, I think, CAL, if I'm not mistaken. And this is diagonal. So diagonal. So in 3 dimensions, length, width, and height. Length times width times height. That is generally the area of some, substances. So this is in 3 dimensions. You will, where does S, how does S look like? So this is the shape of the S orbitals. So let's put this in black color here. So this is the S orbital. These are the p orbitals. These are the d orbitals. And this is the shape of the f orbitals. So the bigger the f orbital is, you see, more the lobes are. So the s orbitals are low in energy, smaller in size than the p orbitals. P orbitals smaller in size than the d orbitals. D orbitals smaller in size than the f orbitals. Okay, so this is the orbitals. Now orbitals means, remember, the house. So that means F has a huge house. So this is a huge mansion. F has a mansion, huge. That is why it can accommodate 14 electrons. And S is a small hut, or a camp, only 1 or 2 people can come in. So that's the deal. And P is like a, mid-size, like a 3-bedroom apartment. And D is also like a big house. Okay, so that's one thing about these orbitals and their energies. Then we also see that energy, this is a low energy. Low energy. And this guy is a high energy. Highest in this case. So we see that the energy increases as you go from like 1 to 4. Okay, when we say energy is increasing, that means the electrons have more freedom to move. Whenever there is more freedom to move, this is where the problems begin to start, where that means they begin to overlap. This is where the overlapping starts at 3D. And that's where you see this mess comes into play. Okay, but we still have to still continue. So we understand these are the shapes. These are the shapes of orbitals. So we see that in this case, look at S. S is spherical shaped, round, circular. P is more like dumbbell shaped. If you look at it, PX, this is PX, where the electrons are found on that side and that plane of the dimensions, and then this is the vertical dimension. So the electrons can be found in horizontally, electrons can be found vertically, and the electrons can be found diagonally in the p orbitals. Okay, similarly here, the electrons have more freedom, more space, so more rooms. So these are all basically rooms. These lobes represent rooms. So the more the lobes, the more space for the electrons is. The more space for the electrons is, more freedom. You see, so here more freedom. This guy again, more freedom. This one, all these different layers, so same is the case. So shapes of the orbitals is one thing, but we see that this one has more freedom is here, more energy and more freedom to move. And the S is less energy and less freedom. Means they're stuck to the nucleus. So we see that as you go from S to P to D to F, the degree of freedom increases. More freedom comes. So let's just put this clearly. This is a little bit not very, so this is more freedom, more energy. Okay, so this is like a theory explaining to you. Now let's look at, fine, we understand, okay, now that S can hold 2 electrons, P can hold 6 electrons, D can hold 7 electrons, D can hold 10 electrons, and F can hold 14. That's fine. We understand all that. So how do we place these electrons in the atoms in the periodic table? So now you just have to imagine that you have on a side a box, and that box contains marbles, and the marbles are representing electrons. And then you have to imagine, the tennis balls, or just, some balls, different size balls, not just tennis ball, but different size of the balls. Okay. So now what you do is you take those balls are representing the nucleus. Okay, so you place the nucleus first of all, because nucleus establishes the identity. So fine, the first column you place hydrogen, then you go to the next one, you place helium, then you come down, you place lithium, beryllium. So you're putting the nucleus basically. Next question is, where are you going to place the electrons? So the first electron is going to, so this is how they are going to be placed, and I'm going to walk you in the periodic table also, but it is best that all of you write this down so that somewhere in your notes also, so you don't miss it. Okay, so here is the first electron is going to go to the first energy level, and in that energy level there is the S subshell. S subshell contains S orbital. Maximum number of electrons that can be held by the S orbitals is 2. So if you have to place one electron, it is just going to be first going to 1s1, and then you stop. But if you have 2 electrons, then they go and fill the 2s. But if you have 3 electrons to place, such as in lithium, what do? You go to the next energy level, and that next energy level is 2s, and it contains 2s like energy, the subshell, and then 2s orbital, and the 2s orbital can hold a maximum number of 2 electrons. 2, the second energy level, also has the p. So if you have more electrons, then you go and fill up the p. Okay, p can hold a maximum of 6 electrons. If you have more electrons, then what do? You go to the third energy level. The third energy level has 3s, and 3s can hold a maximum of 2 electrons. Then after 3 comes the p, 3p. P can hold a maximum of 6 electrons. Now, after 3p comes what? After 3p comes 4s, okay, not 3d. Although that's where, remember, this is where the overlap begins to happen. So this is the situation of overlap. So I'll put this here. This is the overlap situation at 3d, which means that the 4s is going to take a priority. So 4s will fill up first. The 2 electrons are going to fill up the 4s first, and then they go to 3d. Okay. And D can hold a maximum of 10 electrons. So it's available, all those 5 orbitals are available to, and they can each have 10 electrons. Then comes the 4p. And P, 4p can hold, regardless, P, whether it's of 2 or 3 or 4, it doesn't matter. Maximum P can hold is 6 electrons. After 4p comes 5s. 5s can hold a maximum of 2 electrons. After 5s comes the 4d. So let's come down here, 4d. Okay, D can hold a maximum of 10 electrons. Then after 4d comes 5p. And 5p, 6. And then 5p, after 5p comes 6s. So this is where all this overlapping is happening. Okay, after 6s comes 4f. So this is the priority. This is the energy levels. After 4f comes 5d. After 5d, and D can hold a maximum of 10, comes 6p. P can hold a maximum of 6. After 6p comes 7s. S can hold a maximum of 2. You go back down here, it becomes 5f. F can hold a maximum of 14. And then comes the 6th energy level, and that's D can hold a maximum of 10, and so forth. Okay, so here I will just put this here, that you have to go to here. It's this thing is in continuation. Okay, and similarly this. This is continuing. So one thing, students like to put this in a linear format. So it works for them. Other than that, look here on the screen, on my screen, this is the, this piece right here. You see, where is it? This piece right here. This, oh God, this piece right here. So this one is in your handout, okay? And you can basically straighten it up. So I straightened it up like this, okay? But you can do it that also if you like. Now here, what do you see here? Now you see that till this point, it's nice and linear, but 1s2, 2s2, 2p6, 3s2, and 3p6. This is linear, but after 3p comes the 3d. And after 3D comes, after 3P comes, sorry, not 3D, but after 3P comes 4S. And then comes 3D. And then there is 4P. And then comes 4D. And then 4F. You see that? They are all just getting spread out. And let's look at the other ones. The 3D is now here. And stop. D can hold till D only. 3 can hold till D only, not more than that. Then comes the 5S. So 5S is here, then 5P, then 5D, then 5F. You see that? Then comes the 6S. Then comes 6S, 6P, and then 6D, and then you can go further. I mean, we have not, we have not yet, we are still discovering new elements. So this is up till now, we are till here. But if you look at, I color coded it, if you look at it, like how they are jumping now. So this means fine, we understand one thing that we already talked about it here, that for S, so S is lower in energy state than P. P is lower in energy state than D. D is lower in energy state than F, which is fine. Energy level 1 is lower in energy state than energy level 2. Energy level 2 is lower in energy state than energy level 3. Energy level 3 is lower in energy state than energy level 4. But this is also here. 3P is lower in energy state than 4S, and 4S is lower than 3D. Okay, so 3D is a higher energy. This is higher energy. So whenever there's a filling happening, the higher energy ones do not take a priority. The lower energy ones take priority in the order of filling. Okay, so this is the order of filling. But if you look at the periodic table, that periodic table is arranged. That whole periodic table is arranged in a certain fashion. Excuse me. Sorry about that. Okay, now we're going to look at the periodic table and how these things establish themselves here. Okay, so you see in the periodic table, you guys have the group numbers. Okay, group numbers we talked about. These group numbers, they are based on the valence electrons. The valence electrons are the electrons that are present in the last shell. Okay, so all these guys over here, their last valence electron is going to end in the s orbital. Okay, these group numbers, let's do this again. This group number, let's put this in red. So here, group number 1A, group number 2A, right? And this is group number 3A, and I'm not going to put this A all the time. So this is 3, this is 3, this is 4, this is 5, this is 6, 7, and 8. Okay, and this is the A side. A, and let's finish this also. So this is 1 and 2 A's. Okay, so 1A means this has got 1 valence electron. Sorry about that. Let's just do this again. 1 valence electron, 1 valence electron, 2 valence electron that is present in group 1A. This is 2A. Then comes the 3A. 3 valence electrons, 4A. 4, that's why it's getting cluttered. Sorry. 3 electrons, 3, 4, 5, 6, 7, and 8. And these are the electrons. Okay, these are the valence electrons. So valence electrons, VE. Okay, so these are the valence electrons. That's the valence electron. Okay, valence electrons, these guys. Okay, so that's one piece. Next is the group numbers. So based on these valence electrons, we have these group numbers. Oh God, what is happening here? Okay, just do this again. Group number, valence electrons. Valence electrons are the electrons that are in the last shell. So again, I'm going to just put it here again. Group number and valence electrons. All right, so we have the 4 electrons. So this is 3, this is 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, and 8. Group numbers are 5, 6, 7, and 8. And these are A's. Because of the lack of space, I have to do this 3 and 4. So these are the A's here, and these guys are also A. Okay. All right. So this is, let me at least put the electrons so you get an idea. Okay. Besides that, this piece right here, these two blocks and these blocks right here, and these ones over here, and these ones over here. Okay, these are the S block. This is the S block, this is the D block, this is the P block, and this is the F block. So that's the blocks. Block. Okay, now why is it an S block? Because the electrons, the valence electrons, are ending in the S orbital. Here, the valence electrons are ending in the P orbital, all of them. That is why these are called the P blocks. Okay, so that's the P block. Next is the middle one. The middle one is the this ones. So these here, the orbitals are ending in the electron, the valence electrons are ending in the D block, and we'll see it when you do the electronic configuration. And then the last one is the F block. The last electron ends in the F block. When you start placing them, the last electron is going to go in the F block, F orbital. Okay, that's one piece. Next is, so that's about the columns. But what about what about these guys, the rows? The rows are, if you look at, this is row 1, row 2, row 3, row 4, row 5, row 6, and row 7. Now here, the only thing is here, just keep this in mind, that this is actually starting from the 3rd row. This is 3D, and this guy over here is the 4D. Okay, so the starting point. So each of these rows, 1, 2, 3, 4, 5, 6, 7. These represent the energy levels or the shell numbers. Shell number are these. Okay, each one of these, or these are also the energy levels. Like how many energy levels are there? So all this. Okay, now another thing I want to show you. S can hold how many electrons? S can hold a maximum of 2 electrons, right? The orbital is what? Orbital is the place where the electrons are found. That is the probability of finding the electrons is in the orbitals. Okay, so let's put this here somewhere. It's getting very cluttered here, but I'm hoping that, okay, I'll put a note of it separately. So let's put this here. The orbitals means that the probability of finding the electrons in that region, you know, in that place, you know, that place around the electrons, around the nucleus, that the orbital, that is where there's a probability of finding the electrons. And I mean, ideally it is probability, but let's for your course, it's just going to be, let's put it here, that the orbitals are where electrons are found. Where do you find people? You generally find them in their homes. So that's what it is. This is the home of electrons. Okay. Now we know that the s orbitals can hold a maximum of 2 electrons. Okay. So that means there are 2 columns. P can hold a maximum of 6 electrons. So that is why on the P block side, there are 6 columns. D can hold a maximum of 10 electrons. So D block is 10 columns. And F can hold a maximum of 14 electrons. Therefore, there are 14 columns. You can count them. Let's just do this. 10 electrons of D, 10 columns of D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. P has 6 columns because P can hold a maximum of 6 electrons. Where are they? 1, 2, 3, 4, 5, 6. 6 columns, right? S can hold a maximum of 2 electrons. So there are 2 columns. Where are they? 1, 2. Okay, and then similarly for the F. So that's the way, you know, see how intelligently the whole periodic table now makes sense. Now let's start doing the electronic configuration. So just make sure one thing, that the electrons, they are spinning on their axis, electrons spinning in the orbitals. And when they're spinning in the orbitals, they are spinning like this and like that, opposite direction, clockwise and anti-clockwise. Clockwise and anti-clockwise, okay? Like that. Okay, now we will have, so this is what we covered. Now let's start doing the actual electronic configurations. So let's do the electronic. Actually, this is Pauli's exclusion principle. This is Pauli's exclusion principle. When the electrons, they spin in the opposite directions, okay? And so that's the Pauli's exclusion principle, that no 2 electrons can have the same quantum number. So you don't worry about that. You just, you know, focus on that they spin. That's the only way they can remain stable in a in a room, you know, electronic configuration. Okay, now let's look at how are you going to do the configuration of, let's say, hydrogen, then helium, then lithium, then beryllium, then boron, then carbon, nitrogen, oxygen, sulfur, oxygen, and which is the other one? I think fluorine and neon. Sulfur, not sulfur, oxygen, fluorine, and neon. Okay, hydrogen has 1 electron, helium has 2, lithium has 3, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9, and neon has 10 electrons. Okay, so where is the first electron going to go in the case of hydrogen? Going to first energy level, s orbital, and we only need to place 1 electron, so we leave it like that. Helium is 2 electrons, first energy level, s orbital, and those 2 electrons go to the s orbital. Finished. 3 electrons in lithium. 1 electron goes to, no, first 2 electrons go to the first energy level because s can hold a maximum of 2 electrons. So s gets filled first. Now you're left with 1 more electron. So you go to the next energy level, and here s, and then s has 1 electron. Okay, next is the beryllium. Beryllium is 1s2 and 2s2. Boron is 1s2 and 2s2, and there's 1 more, so this go to the remaining 2p1. Okay, 2p1. Carbon, 1 energy, first energy level, or the first shell, then the first subshell, then the first orbital. The first orbital is 1s, 2 electrons go here, the remaining 4 electrons go to 2s. 2s can hold a maximum of 2, and you're still left with 2 more electrons, so you go to 2p2. Okay, nitrogen is 1s2, 2s2, and 2p3. Then oxygen, 1s2, 2s2, and 2p4. Then fluorine, 1s2, 2s2, and 2p5. And then comes neon, 1s2, 2s2, and 2p6. Okay, and you stop. Then after neon, if you have to, let's say for example, sodium. So you have sodium has 11 electrons. Here's your sodium, 11. And then comes magnesium. Then comes aluminum. Let's keep going. Magnesium, 12. And then comes aluminum, 13. And then comes just like silicon. Silicon is 14. And then comes phosphorus, 15. And so forth. Okay, so here let's look at the next pattern. So we are going to look at the patterns. Okay, so here we have 1s2, 2s2, 2p6, and 3s1. Now you must be wondering, why is it she's stopping at 3s1? So I'll show you that also. But look at this, 1s2 for 12, magnesium 12. So 2s2 and 2p6 and 3s2. And then comes aluminum, 1s2, 2s2, 2p6, 3s2, and 3p1. Silicon, 1s2, 2s2, 2p6, 3s2, and 3p2. Then comes phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Okay, now here are a few things. First of all, why do you stop at a certain number? There are few things, like for example, look at boron. Where is boron found in the periodic table? Boron is found in the second energy level. Boron is found in the second energy level right here, 2. This is the 2. Let's put it in another color. Wait 1 second. Boron is here. Here, 2. So in the second energy level, right? If you look in the periodic table, boron is present in second energy level, P block, and it is present on the first column in the P block. So this is what it means, that this is boron is present in the second energy level or second period, and this is also found in the P block, and in the P block it is at first column on the P block. Okay, so that is why second energy, P block, first column. Look at carbon. Carbon is found in the second row, again, second column, right? Second column, but on the P block side. So second column means P2, and this is where you see P2. Second period, P block, second column. So let's write this down. For carbon, second period, P block, second column. Second column in P block. Pay attention to that. Second column in P block. Okay, now look at the third one. Let's look at the third one. This means it is in the third column in the P block. This is P and then. So if you look at nitrogen, where is nitrogen found? Nitrogen is found in the second period, and yes, it's found in the fifth column, but look at the P block. In the P block, it is found in the, in the P block, it is found in the third column. So it is going to end in 2p3 right here. 2p3. Okay, same is the case with oxygen, 2p4. Oxygen is right here, second energy level, fourth column in the P block. This is important, fourth column. So let's put this here one more time, and then after that we'll move further. So oxygen is found in the second period, and it is found in the P block, and in the P block it is found in the fourth column. It is placed in the fourth column, and the fourth column is here. The fourth column where the sixth block is. Okay, and then similarly for this for fluorine, and same is the case you would do for all the others. Okay, and that's neon. So same thing, you know, I don't want to embed this, but this is where that is where you stop. So how do you determine where to stop? Let's put it here. How to determine where to stop. So look at the period, block, and column number. And that's what it is. So boron's case becomes boron's case is boron is 2p1, 2 second energy level, 2p1. Carbon's is 2p2, and oxygen is 2p4, 2 2p4. Okay, so this is one thing where, you know, students ask this question. Okay, now let's look at some of the other interesting things. Look at some of the patterns. One of the pattern is that, yes, S block ending in S. So this guy actually, because it's a noble gas, so it is kept with the noble gases. Kept with noble gases. Okay, but if you look at it, this is in S block, first column, right? And this number on the top also relates to the group number. And this is the valence electron. Okay, now look at this in here. 1s2, 2s2. Valence electrons are basically, this is one concept of energy of doing this. Second one is the valence electrons. Valence electrons are the ones that are found in the largest shell number. So valence electrons are found in highest shell number. So just don't forget that. Highest shell number, or you can also say the same thing is the energy level. It means the same. Or some say principal number or principal energy level. It means the same. Okay, the shell number. So where is the valence electron? Valence electron is in the energy level 1, and there's only one valence electron. Okay, so this number, so in this case, let's look at this one. 2s1, so this 1, that means it is also present in that column in the periodic table. Okay, so that's the group number, the valence number, sorry, and then this also is the, yeah, so this is the group number 1a, right? And that's why it has got one valence electron. Okay, this guy is present in group 2a. So this has got two valence electrons. Now this is 2s2 and 2p1 together. So there are total of 3 valence electrons. And it is present boron in 3a group number. This piece right here, all of them are 4 valence electrons. So that is why they are present in 4a. This piece 2s2, 2p3. So 2 plus 3 is 5 valence electrons. Okay, valence electrons. That is 4a. That is 5a. Okay, this is 2 plus 4 is 6. Okay, so this is 6 valence electrons, and that is in group 6a. 5 plus 2 is 7. 7 valence electrons. So this is present in 7a. 6 plus 2 is 8 valence electrons present in group 8a. Okay, so this is very important. Okay, so this piece right here is just the last shell. This is the last shell. This is the last shell. This is the last shell. So keep that in mind. Now, and then valence electron is also the highest energy level. This is also the last shell or last energy level, where the electron is, the last electron goes. Okay. All right. Next is the concept of, so if you look at it this way, this is one, and this is in one means one valence electron, and this is in the third energy level or the third period, but it is in the first column. Okay, group 1a, group 1a group. Okay, 2 valence electrons, 3s2, only 2 valence electrons. That is why this is present in group 2a. This one is S2 and 3. So all of this together. So this is 3 valence electrons. So 3A. 4 valence electrons. 4A. 5 valence electrons. 5A. Okay. All these notes I'm writing, I hope these are clear. But there's a lot of information, right? So it's best that you guys also should, oh God, I deleted that accidentally. 3s2 and 2p5. Okay, so this becomes, this is 7 valence electrons, 6 valence electrons. Okay, now there's another piece. This is a lot the way we write. So we can condense it and write it in the noble gas configuration. Noble gas configuration. And then we are also going to look at the orbital diagrams. All right, look at a noble gas configuration first of all. Noble gas configuration is the condensed version. Condensed electronic configuration. Electronic configuration. Okay, so let's look at one more time. Let's, for example, sodium or magnesium. Sodium, magnesium, and aluminum. Let's look at that. Sodium, 11 electrons, 1s2, 2s2, 2p6, and 3s1. There's another thing I want to point out. When you add this up, 2 plus 2, 4, plus 6, 10, plus 1, 11. So when you add these electrons, add electrons, and that comes out to be 11 electrons. So that's another thing that tells you whether your configuration is correct and whether, So now here's another thing. Look at the inner core. This inner core, 10 electrons. These 10 electrons, neon has 10 electrons, right? So the inner core can be written as neon, that is of neon, 10 electrons and 3s1. Okay, 3s1. So that's one way of writing these. And another thing is the Lewis structures also. We will look at that a little bit later, but let's look at another example of magnesium, 12. So same thing, 1s2, 2s2, 2p6, 3s2, and you stop. Why do you stop? Because if you add 2 plus 2, 4, plus 6, 10, plus 2, 12. So that's where you stop. But now let's look at this piece. This piece here, the 10 electrons. These 10 electrons are representative of neon, the nearest noble gas, 10 electrons, and the leftover last one is 3s2. Okay, so this is the condensed form. All right, now let's look at the Lewis structures, and then we will look at the D blocks. But let's look at, first of all, the Lewis dot structures. Lewis structures. Now, Lewis structures, we focus only on the noble, on the valence electrons. So the focus is only on valence electrons only. Okay, so here's something you should write a note here, that group 1A. So Lewis dots are just dots, right? So this is dot. Okay, so group and dot, or rather groups and valence electrons and dot. So whatever the group number is, so this is group 1A, 1 valence electrons, 1 dot, only 1 dot. 2A, 2 valence electrons, 2 dot, 3a, 3 valence electrons, 3 dot, 4a, 4 valence electrons, 4 dot, 5a, 5 valence electrons, and 5 dots, 6a, 6 valence electrons, 6 dots, 7a, 7 valence electrons, 7 dot, 8a, 8 valence electrons, and 8 dots. And then I also have another piece, which is the transition elements. Okay, transition elements, which are the D blocks. For the most part, all the D blocks will have 2 dots. And they also have variable. It could have more, but generally, their valence electrons are 2. So, just keep it like that. Okay, so let's look at it. Group 1A. If in group 1A, there is group 1A, let's look at sodium. For example, sodium will have only 1 dot. Then comes magnesium. Magnesium has 2 dots. Then aluminum. Aluminum has 3 dots. Then carbon. Carbon has 4 dots. Then comes the 5th group is the nitrogen. Nitrogen is 5 dots. So 2 here and 3 on one side. This is oxygen. Oxygen has 6 dots like that. Then comes the chlorine. Chlorine has 7 dots. 3, 4, 5. And then comes the neon. Neon has, no, sorry, argon or neon. So did we do this, all this? Okay, I covered, okay, carbon. So, let's say neon. Neon will have 8 dots. So all the noble gases will have 8 dots. Okay, so that's one piece. So you guys can make this based on the valence electrons. Now let's look at the electronic configuration in D blocks. Electronic configuration in D blocks. D block element. Like for example, there are copper. Let's do some other one. Not copper. I'll do copper and iron. Let's do nickel. Nickel. Okay. So nickel is 28. So we need to place 28 electrons. So first of all, where is nickel found? Nickel is found in 3D and it is found in the 8th column. 3D8. That's where you need to stop. Why? This is found in the 3rd row. It is found in the D block. And it is found in the 8th column in the D block. Okay, so that is why you will be stopping at 3D8. Now let's write the configuration. So all you need to do is sometimes go back. Remember, why did I say 3D? So remember, this thing starts at after. So this is officially 4th column, no, 4th row, sorry, 4th row, but with the D blocks, they start with the 3D, and then the next, it starts, there is a fifth column, no, sorry, the 5th in the 2nd, look at the 1st and 2nd columns, 5th row, but the 5th row, once it hits the D block, the transition elements, it's the 4D. It starts with 4D, okay? So that's one piece you can do. Another thing you can do is you can just simply follow this linear pattern as you see on the screen, if that works for you, okay? So another one is, using the periodic table, which is first fill up all the S block, then go to the P block, then come back to the S block, then, depending upon, how it is, then you keep going and you just follow those blocks. Okay, so let's do this one for nickel 28. So nickel 28, 1s2, 2s2, 2p6, 3s2, 3p6. This is standard. But remember, after 3p comes the 4s. So here is your 4s2 and then 3d8 and you end. So if you add these guys right here, okay, so this is 18 electrons and these 18 electrons represent argon, so which is a noble gas. So you can also write this as argon in square brackets 4s2 and 3d8. 4s2 and 3d8. So here we see that even with that largest, this is the valence shell. Valence shell. And valence shell is the highest shell number or the highest energy level. Okay, energy level. All right, so that's the electronic configuration of nickel. Okay, so what is the valence of nickel? It's 2. The valence electrons are 2. So 2 valence electrons. And this is this. All right, so that's one piece. Next is, let's look at another one, which is, let's do chromium. Chromium. So this is one example. And this is the second one. Okay, chromium is 24, and this is found in the third period and in the D block, and it is found in the 1, 2, 3, 4 fourth column in D block. Okay, so what do you get here? That means it is going to be 3d4, and this is going to where it is going to end. So 1s2, 2s2, 2p6, 3s2, 3p6, okay, 4s2 and 3d4. All right, so same thing. This piece right here, 18 electrons, can be written as inner core argon, and then you close the with the inverted commas. That's 18 electrons have been accounted for, or inner core. This is the inner core electrons. Inner core electrons. Okay, inner core electrons are internally placed. Then comes 4s2 and 3d4. But even with this placement, this guy is the valence shell. So don't forget that this highest shell number, valence shell, and it contains 2 electrons. So when you make the electronic configuration of the Lewis dot structure of chromium, it will just be these 2. Okay, same story here. When you make the electronic configuration of nickel, nickel is also going to be like, sorry, the Lewis structure is just going to be 2 dots. Okay, now let's look at some other situation, which is the special situation, special. Okay, so for example, copper. Copper is 29. Fine, it is in the 3rd period. D block, even in the D block, it is in the 9th block, you know. So that's one thing. So now let's start doing this. Copper 29 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d9. Now, fine. There is a rule called half-filled, and full-filled orbitals are more stable. Okay, and this is Hund's rule. So the problem is this guy has 9. So in that case, the copper would want to make 2 electrons. Sorry, the copper would, sorry, what am I saying? The copper would want to have, like copper wants D9 to have D10. So then it's a very happy boy. Okay. If it gets that, and this is going to happen. So copper will have copper 29. Let's go back and show this. Argon 18. And you have 4s2 and 3d9. So in normal conditions, yeah, you know, this is the scenario, but what happens is, let's draw the orbital diagrams to show this. So orbital diagrams. Orbital diagrams are 4s2 and 3d9. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These are the 5 orbitals. Remember, D will have 5 orbitals. D orbitals will have 5, like D subshell will have 5 orbitals. And P subshell has 3 orbitals. S subshell has only 1 orbital. Okay, F subshell will have 7 orbitals. But we are only dealing with the 3D9, and this is the 4s. Okay, so 4s is only 1 orbital. Now look at these electrons. 4s2 is right here, and 3d9 is first you fill in 1, 2, 3, 4, 5, 6, 7, 8, and 9. So always when you're making the orbital diagrams, always singly fill all the electrons, or singly fill all the orbitals. Okay, first fill all the orbitals like singly occupied. Then start pairing. Okay, from left to right. From left to right. Okay, so that's how I paired it. But here's fine. This is what happens with the copper. Copper in this condition is not happy. It wants the D to get 9. So what's going to happen? This electron jumps and comes here. So this is the internal jumping happens. Internal jumping. And when this internal jumping occurs, a new arrangement happens, which is like this. So 4s, and then this is 3d9. 1, 2, 3, 4, 5. And now we have half filled. Did I write this down? Full-filled and half-filled. Half-filled and full-filled orbitals are more stable. Okay, so half-filled 4s, and then fully filled 3d. And see how I'm doing this. I'm first singly occupying them, and then I'm pairing them. So all of them now are paired, and they are very happy. Okay, and here they are not happy. Okay, so this internal jumping makes them more stable. So we have, this is 4s1 now, but this is 3d10. Okay, so this is the orbital diagrams and internal jumping. And then also copper, you're going to study, and I'm going to talk about it. I don't want to take in too much of this time here, but here is the D blocks. And let's see if I left anything. And, ideally, you guys also need to try these out, and you will be then fine. Yeah, I did this. And then let's do let's do for lead. Just want to do this for lead. So electronic configuration of lead. Okay, lead. Okay, this is the last, and then we'll do the trends, and then we'll end. Okay, lead. So where is lead placed? Lead is placed in the sixth row, and it is on the P block, and it is in the second column. So sixth row or sixth period, and it is on the P block, and it is in the second column. Okay, that is this substance called lead. So lead contains 82 electrons. 82 electrons. So let's start placing these 82 electrons. So lead 82, and at least we know we need to stop at 6p2. Now, remaining thing you can just follow all the way. You can just follow this as I'm explaining this. 1s2, 2s2, 2p6, all the way till 6, wherever there is 6p, right here, 6p. Okay, so that's where you have to stop, but remaining you can just copy the rest of them. Okay, so let's do this here. All right. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, okay, 3d10, then 4p6, then 5s2, then 4d10, then comes 5p6, then comes 6s2, then comes 4f14, then comes 5d10, and then comes the 6p2. And if you count these, you will see this 2 plus 2, 4 plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 2 is 50, plus 10 is, plus 6 is 56, 56, and then 14, 10, and 2. Let's count this. 56 plus 14 plus 10 and 2. So what do you get? 10, 2. So 5, 6, 7, 8. 82 electrons. All of them got accounted for. Okay, so the whole thing can be condensed. Now here, the nearest noble gas for lead is xenon 54. Xenon 54, the nearest noble gas. Nearest noble gas is xenon. Okay, and xenon is 54. So xenon 54, and then the remaining all the way till 82. So let's see where's the xenon coming in. Xenon comes in these 5p6. So right here till here. Okay, so then after that is 6s2. No. Xenon is Lead is 6p2 and xenon is 5p6. Did I get this right? 54. Let's see. Let me do this one more time. So 1 minute. Okay, so here's the situation with the lead. So we got a xenon covered till here. I was just messing up with the counting, I think. So this is 54, and that's xenon is accounted for. And then the remaining ones are 6s2, 4f14, 5d10, and 6p2. So the remaining ones you're going to write here. But now pay attention. Which ones are the valence electrons? The valence electrons are every electron that is found in the largest shell number. So 6s2, 6p2 is the valence shell. Okay, and that contains how many electrons? 4 electrons are present in the last shell. Okay, and if you really look at it, lead is also found in group 4A. Lead is in group 4A. So technically it should have 4 valence electrons, and that you can see. All right, guys, so this was, simple, these type of questions that I asked. And if we can ask also like, okay, draw the orbital diagram of the valence electrons. So you're just going to do it, that 6s2 and 6p2. So how will you show this? 1, 2, 3. These are the three. These are the p orbitals. And p orbitals are always going to be 3. This is the s orbitals. This is the 1s orbital. All right, so now you are going to put 3s2, 6s2 here. This is the 6s2, and this is the 6p2. 6p2 would be here. So do not pair. Do not pair. So leave them like that. Okay, this means that lead can exist as +2 state and lead can exist as +4 state, but we will study that in the next chapter. But that's one piece. Now there comes the last piece, is the trends in the periodic table. Trends in periodic table. All right, now there are 3 major trends. One is that relates to the size. And when we talk about size, we are actually looking at the radial size of the radius. One thing. Next is we are looking at the electronic, sorry, not the electronic. We are looking at the ionization energy. Ionization energy is the energy that is given to release the electrons. Okay, ionization energy is the energy given to release electrons. Okay, and it relates to also electron affinity. Electron affinity. Electron affinity is love for electrons. All right, and then we also have the metallic character, like the size is increasing. So metallic character increases or decreases, means acts more like a metal. So let's look at the where's the handout? Okay, so handout. Okay, so if you look in your handout, you will see that the here. All this page relates to the electronic configuration. So like I said, some people like to do this electronic configuration based on this type of, preferences. That's fine, they can do that. Now we are looking at the trends in the periodic table. So in a periodic table, when you move from left to right, the metallic character increases. When you go from top to bottom down in the same column, the metallic character is increasing. So that's one piece. Let's write this down. That the, metallic character, let's do this first, that so here is this, when you go from right to left, okay, and when you go in the same column from left, like from top to bottom, then yes, the metallic character increases. So as you move, see the direction of the arrow. So as you move from left to right and moving from top to bottom. So this piece is going to be the most metallic. Okay, and as you go, so this is, here is anything that is on this side of the group of the periodic table is less metallic. All right, and everything else is in between. So that's one piece. So let us see, if you are given simple questions like a question is given like nitrogen versus lithium, which one is more metallic? So you identify the placement of nitrogen on the periodic table. So nitrogen is less metallic than lithium. Lithium is more metallic. Okay, more metal-like. Next is, you are given phosphorus and you're given magnesium. Which one is more metallic? Magnesium is more metallic than phosphorus. Phosphorus is less metallic, and so forth. Okay, so just follow that. Next is the ionization energy. Ionization energy is the ability to, the energy that is given to remove the electrons. So energy given to an atom to remove electrons. Okay, and that relates to the electron affinity. Electron affinity. Electron affinity. So I'm going to put this as IE and electron affinity as EA. Okay, so the electron affinity is obviously the attraction, love for the electrons. So love for electrons. All right, so when we see that from here, you see the trend in the ionization energy. So it would be very difficult to remove the electrons that are on the right-hand side of the periodic table. Same is the case, the electrons would be can easily be removed in a same column. When you go from bottom to top, the bottom ones do not have a strong ionization energy, means they can easily release the electrons. So basically the amount of electrons, the amount of energy that you give to the electrons, that is the ionization energy. So, sorry, we have now the, let's draw this here. Here, you go from bottom to top and you go from left to right and bottom to top. All right, so this means that this guy will have very large ionization energy. very large. To remove an electron, the amount of energy that you're giving, that is very large. This guy will be at the bottom, will have very low ionization energy. Okay, so if you're given two molecules, two atoms, and you're asked to compare, tell which one has a higher ionization energy, aluminum versus phosphorus. Aluminum versus phosphorus. Which one has a higher ionization energy? So aluminum will low and phosphorus will have a higher. So this is higher ionization energy. Okay, phosphorus. Next is, let's look at oxygen versus beryllium. Oxygen versus beryllium. Which one has a higher ionization energy? Oxygen will have a higher ionization energy than beryllium. Beryllium will easily lose electrons, but oxygen has a strong electron affinity. Okay, and that means the ionization energy is very high. Okay, so ionization energy high, and then so ionization energy and electron affinity very high, relate to each other. Higher the ionization energy, higher the value of electron affinity is. Why would they lose electrons if they love electrons so much? You know, so these guys love electrons very much. They don't let the electrons go. So one thing I'm going to add here is that their and electron affinity is also very high. Okay, so they have lower electron affinity. Okay, so keep this in mind. All right, and the last one is the size, and the size is the radial size. Radial size. Size of the radius. So what is that? Radial size is the radius. Okay, now in the same period, going from left to right, okay, the size is decreasing. Size comes down. Okay, so if you were to compare the size of sodium versus chlorine, both of them are in period 2, second period. So when they are in the second period, we see that sodium is bigger in size than chlorine, because both of them have the same energy level, but larger nucleus. So attraction, the nuclear pull, the attraction of nucleus is very high. Okay, so therefore electron cloud condenses. Condense means it shrinks. Okay, it shrinks, and when it shrinks, the size, that is the radius becomes small. All right, guys, so that is the situation with chlorine. What's happening with chlorine? Why would chlorine have smaller size? Because of that, because the further away you go from, in the same period, you have the same energy level, you are just adding more electrons. More electrons means more protons. More protons are added in same row or same period. Okay, so therefore the nuclear pull always is going to increase, and when the nuclear pull increases, that means the size decreases. The size of the atom, the radial size, sorry, I mean the mathematically it won't, but the radial size decreases. Okay, so I've written all this, and in case I left out something, you're always welcome to ask me, but I covered everything from this chapter much in detail. So please spend some time, revising and reviewing this and doing this yourself, applying all this yourself. I covered a lot of theory, okay? And don't hesitate to ask me any questions. Okay, guys? All right. Okay. Thank you for watching. Good night now. Bye.